This part continues the discussion we began in the last part of infrared radiation, IR emission. I'll remind you that the rate at which thermal energy is broadcast away from any object is governed by this equation. R, measured in joules per second, equivalent to a watt, is equal to Stefan's constant. It's a number I gave you last time. We won't need it in this lesson. Times the emissivity E. That's a number that is a measure of how efficient the surface is in radiating energy. It's a number that's dimensionless and ranges between almost 0 to almost 1, but never exactly 0 or exactly 1. A is the area of the surface of the object, measured in square meters. T is the Kelvin temperature, and it's raised to the 4th power. So small changes in the Kelvin temperature can have an enormous impact on the amount of IR emitted from the object. Consider this example. In the first place, the rate of emission from an object, symbolized as R1, is given by this equation, where T is the Kelvin temperature in the first instance, in the first case, and the rate of emission is 10 watts. We ask the question, in a second situation, the same object, what would happen if you tripled the initial temperature so that T2, the later Kelvin temperature in the second case, is 3 times T1? Well, here's the rate equation for the second case. Put a subscript 2 on the R and a subscript 2 on the T. It's the same equation as here, except change the subscript. Well, we replace T2 in this equation with 3 times T1. Three is raised to the 4th power in this parentheses. It's 3 times 3 times 3 times 3. 3 times 3 is 9, and another 3 times 3 is another 9, so final result is 81. I pull the 81 outside, put it in front, and we have 81 times that parentheses. Look at this parentheses with the subscript 1. It's the same expression shown up here. So we may replace this expression down here with 10, and I do that over here. Final result is that the new rate of emission of infrared waves is 810 watts. Now, the next example is similar. Suppose, again, we start with 10 watts radiated from some object, but we reduce its temperature to 1/2 of what it used to be, and then we replace the temperature T2 that would ordinarily occupy that space raised to the 4th power with 1/2 of T1. Well, now we have 1/2 raised to the 4th power. That's 1/16 times that parentheses, which again is given back here as 10 watts. Final result, 10/16, and you could simplify that to 5/8 of a watt if you felt like doing that. I'll see you next time.